I'm Paweł Idziak from Jagiellonian University, and I'm going to present a joint result with my co-authors on some intermediate problems in modular circuit satisfiability. The project itself started with probably the most interesting problems in mathematics, like solving equations. All we do know that linear equations can be solved shortly or fastly. The Diophantine equation cannot be solved algorithmically at all. You know, a big part of mathematics, like Galois theory, was created. For us, maybe the most interesting example is satisfiability of Boolean formulas. In this talk, we'll concentrate, we'll leave the realm of Boolean algebras, and we will concentrate on finite algebras, where the issue is not the decidability but the complexity. And we want to know how fast equations built up from polynomials can be solved. By a polynomial here, I mean a term in which some variables are replaced by constants. Our research project is to characterize those algebras, those finite algebras with finitely many operations, for which there is a fast polynomial time algorithm solving those equations. A brute force algorithm obviously requires exponentially many evaluations and is not good enough. However, the problem that arises here is in what terms such classification is even possible. The other thing is that this problem seems to be pretty much connected with constraint satisfaction problem, which has been already solved a couple of years ago by Bulatov and Zhuk. But as we can easily see, it's the connection between those problems is not full. In a sense, if you consider the system of equations where the external conjunction is present, then it can be bisimulated by constraint satisfaction problems. However, when you restrict to a single equation, then to interpret the external conjunction, you have no freedom to replace those atomic formulas in CSP by consecutive equations. Instead, you have to squeeze these external conjunctions in the polynomial or term. And that's a kind of problem, and we will see that under some complexity assumption like exponential time hypothesis, this in fact cannot be done. But starting with such kind of projects where the characterization of arbitrary algebras is needed, let us look at some classical examples like groups or rings or lattices, which in a sense, as we will see, play a role of some paradigms in general situations. So for groups, we know that a problem can be solved in polynomial time if the group is nilpotent and it's NP-complete for groups that are not solvable. There is a gap between those nilpotent and non-solvable groups, and I will talk about that at the end of this talk. For rings, that's simply because everything which is solvable here is nilpotent. We have a nice splitting between the polynomial time rings, I mean nilpotent rings, they are rings without unit, and NP-complete ones which are not nilpotent. For lattices, the splitting here is between distributive lattices and all the others. So there are no many lattices as well with a fast algorithm for solving equations. The problem, however, here is that if you want to get a characterization that it, in general situation, not like in groups or rings or even lattices, you don't know which operations fix as fundamental ones. For example, in groups, already the group S3, the symmetric group on three elements, in its original language with multiplication, is in p time, while if you add some actually definable in terms of multiplication and inverse additional operation, it's NP complete. That's simply because these additional operations may be then used to shorten the size of the input. And here is a picture that shows you that in that for this commutator term at the top of the slide, its size in ordinal signature with multiplication is of exponential size, while if you add a binary commutator here, then it's of polynomial even linear size. So what we do, we replace equations by circuits. So instead of considering a term or a polynomial as its syntactic tree, we replace it by a circuit. And now, instead of having on input two polynomials, we have two circuits. Or two output gates in one circuit, and we ask if they return the same value for the last problem on this slide, and every time, or just sometimes if we consider satisfiability. So going back to groups, we see that even circuit satisfiability problem is NP complete for non-nilpotent groups, and in p time for nilpotent groups, which simply shows or closes the gap I mentioned before in this language, where those shortenings are possible. What is open, however, is still how to fill the non-nilpotent but still solvable groups gap. We leave the realm of groups a couple of years ago, and we got a result in a very broad setting of so-called congruent modular varieties that obey groups and their extension like rings or Lie algebras or whatever, and lattices which also contain their extension like Bulan algebras, Hating algebras, and almost actually all algebras considered in logic. The prominent exception which doesn't fall into this realm are semigroups. And our result we presented at this conference 2 years ago was that two kinds of structures actually lead to polynomial time algorithms. They make the problem tractable. The one thing is super nilpotency, which is the condition that is stronger than nilpotency. However, in groups, it's the same. This concepts coincide with nilpotency, and also the distributive lattice-like behavior. It's fast to solve. We showed that this can be generalized, but also we showed that a partial converse to it. So that circuit satisfiability for algebras from congruous modular varieties, which cannot be expressed as a product of nilpotent algebras and distributive lattice-like algebras, is NP complete. Still, as we see, there is a gap between nilpotent and super nilpotent algebras. Both super nilpotency and nilpotency they generalize this concept of nilpotency in groups and rings, where, as I already said, they do coincide, but in congruence modular settings, super nilpotent algebras are nilpotent, but not conversely. And actually, we created two nilpotent, but not super nilpotent algebras with polynomially time solvable constraint circuit satisfiability, which shows that leaving the super nilpotent realm, there are still structures solvable in polynomial time. And some philosophy about it. So in the point why super nilpotent algebras has fast algorithm for satisfiability is that conjunction-like terms or polynomials have actually a bounded arity. Nilpotent but not super nilpotent algebras do have conjunctions of actually arbitrary large arity, but unfortunately this polynomials that behave like conjunctions have super polynomial or even exponential size with respect to its arity. What we do is the algebra is nilpotent. The algebra is not super nilpotent. So we want to measure the failure of the super nilpotency, and we want to split the congruence lattice of this algebra, or if you look at groups, the normal subgroups of such a group, into some intervals which are in fact super nilpotent locally. And the smallest number of such super nilpotent intervals that can be obtained in this way measures the distance from super nilpotency. In particular, for super nilpotent algebra, this is just 1. What we observed here is that the failure of super nilpotency, or actually the interplay between those super nilpotent intervals, reduces to the fact that we have different primes in those intervals appearing as characteristics of, in a sense, some kind of affine structures that are built into the big picture in those algebras. With the help of such alternation of primes, we can shorten the conjunction. So in fact, if we have two different primes, one over the other, then we can build a conjunction like polynomial, but of exponential size. If we have a longer chain of alternating primes, then we can shorten the conjunction by simply, so for example, for three such primes, by simply taking the square root of n conjunctions with arity of square root of n. This leads to a smaller size of the conjunctions. So more alternations gives a shorter conjunction. Now, the exponential time hypothesis gives a plausible lower bound for nilpotent but not h-step super nilpotent algebras from congruence modular variety. So in such a case, we simply conjecture that there is no faster algorithm that 2 to the polylog of n, when this polylog or degree of this polylog depends on the length of alternating primes. To illustrate this phenomena, we construct a very simple algebra, which is a paradigm for h-step super nilpotent things. That's simply an abelian group, a product of the abelian groups with alternating primes. So P1 differs from P2, P2 from P3, but P3 can be the same as P1. which additional action, which essentially codes the action of consecutive groups. Such structures is not longer abelian, but it's still nilpotent. Essentially, this particular algebra is exactly a H-step nilpotent. The satisfiability problem here is pretty much connected with satisfiability of modular Boolean circuits. So by CCM circuit, I mean the circuits in which modular gates counting the number of ones on input, but here we stratify it with primes. So our assumption is that on the ith level we have only the gates that count modulo p sub I. And our second complexity assumption is this time exponential size hypothesis, which simply says that if you want to get the Boolean conjunction AND with n input gates and model in such CCP1PH circuits of depth H, then essentially that cannot be done faster than we already observed. So 2 to the appropriate root of n. With both those hypotheses, so exponential type hypothesis and exponential size hypothesis, we can give a lower and upper bound. A lower bound for this particular algebra is 2 to the polylog of size of the input circuits. We also have a deterministic algorithm that almost matches this complexity. I mean, there is a difference in the degree of polynomial in the exponent by 1, but we have the probabilistic algorithm with the polylog complexity in the exponent, where the degree of this polylog is exactly the same as the lower bound. Here comes the first conclusion of this talk, that simply because for this particular algebras, the problem under those complexity hypotheses are intermediate, we do not have dichotomy for circuit satisfiability like there is one for constraint satisfaction problem. So in particular, it shows that there is no equivalence between constraint circuit satisfiability and constraint satisfaction problem. Again, in contrast with a system of equations of system of circuit satisfiability and CSP. In fact, because of the existence of translation one side, which I mentioned at the very beginning of this talk, circuit satisfiability has a strictly bigger expression power than constraint satisfaction problem, by which I mean there are problems that are expressible by one equations, but cannot be expressed as a constraint satisfaction problem. The obvious question here is how to treat the algebras in general. So our paradigm algebra can be controlled simply because it's artificially created so that everything can be shown in a pretty nice way. In general, we may have different primes on the very same level. Here on each level, I mean the algebra we have considered before, on each level there's exactly one prime. Now we can have many primes. So this may correspond to CC circuits, modular circuits, in which on ith level there is a set of primes that can be used as modular in modular gates. And a precise analysis of the interaction between those sets is needed. What we already noticed is that higher circuits, so bigger H, or deeper circuits, leads to shorter conjunction-like polynomials. Also, wider circuits, in a sense that more primes are admissible at the very same level, is helpful to shorten the conjunction-like polynomials. And as we already mentioned, shorter conjunction-like polynomials give a bigger complexity. So in particular, in a sense, if the conjunction has a polynomial sign that can be used to code usual SAT problem to prove NP, even NP completeness. And the research in this direction is on the way. Our techniques are also applicable for groups here. As I said, if you take the usual equation in ordinal language of groups, this problem for nilpotent groups is in p time, for non-solvable is NP complete, and we do have a gap between them. In fact, there is no solvable group known to have NP complete problem of solving equations. On the other hand, in this area between nilpotent, I mean of not nilpotent but solvable groups, there are quite a few groups known to have Polsat in solvable in polynomial time, but all of them have so-called fitting rank exactly 2. Fitting rank 1 is equivalent to be nilpotent 1. Fitting rank 2 is equivalent to be, in our language, 2-step super nilpotent. Actually, S4, the symmetric group on 4 elements, was the smallest group for which the complexity of solving equation was undetermined, but our method is applicable to this particular group, and it shows with the help of exponential time hypothesis the lower bound, which is 2 to the square of log of the size of the input. Armin Weiss simultaneously and independently showed that in fact all 4-step super nilpotent groups and some 3-step super nilpotent groups solving equations is not in p time, again with the assumption of exponential time hypothesis, and he is going to present this result on iCalb this year. We combine our effort with Armin, and now we can show that essentially, if the group is not 2-step super nilpotent, so is at least 3-step super nilpotent, then the problem is outside p time, again unless exponential time hypothesis. But what is even more interesting, the 2-step super nilpotent groups are left open, but among them, for example, the dihedral group of 15 elements, so the symmetric group of the 15 angle pentagon has this Polsat problem outside p time, again unless exponential time hypothesis. Thank you.